Okay, the light spectra, really important concepts that the amount of light absorbed by water or transmitted by water varies depending on the type of light. And so you can see that water transmits the blue and some of the green, and then doesn't transmit the red very well. It's absorbing the red and orange wavelengths, okay? And so UV and blue and green light get transmitted by water, but not red or infrared very easily. And so this influences what lakes look like. So if you're a very oligotrophic lake, you're going to transmit that blue light to very deep depths, and that's going to give you a very blue hue. If you're a mesotrophic lake, you know, some productivity, kind of turquoise blue, you're going to transmit more of the green light, versus a very eutrophic lake, you're basically just going to look green. Okay. So light transmission is a function of color for these different types of lakes. And here's Crater Lake from space, not from space, but from a plane probably. It's the second clearest lake in the world. Only Blue Lake in New Zealand is clearer. And it is basically, it's also the 7th deepest lake in the world. And if you go to the deep spots, you can just get almost it's like a pool of distilled water practically. And so oceanographers will bring their equipment to Crater Lake to calibrate it. Basically, they're like, where can I go to get, 500 feet of distilled water? Well, someplace like Crater Lake. So it's a really cool place. And this is called Wizard Island. You should all visit Crater Lake once we can all visit things like that. All right, so here we can see the different transmissions for different light spectra. This one's for pure water, and you can see that it transmits the blue and the green. This is basically a green algae slurry, and it does not transmit the blue and the green. It transmits the red, so it's taking up those blue and green wavelengths and some of the yellow, okay? Here is a cyanobacteria, microcystis, looks kind of similar to the green algae. And here is water that's been steeped in humic substances, almost like tea, right? So a lot of brown, tannin-rich stuff. You can see it does not transmit the blue light very well, but it does transmit the red light. So these different spectra are really important because different lake systems will have different combinations of water and organisms and humic substances that will all influence how light will penetrate. Okay, so an oligotrophic lake has blue water. A lake with green algae appears green. A lake with cyanobacteria appears kind of blue-green. And a lake with high levels of dissolved humic substances will appear reddish-brown. And it's partly because of these abilities to transmit and absorb different types of light. Just like, although I'm not wearing a good shirt, just like if I was wearing a red shirt, that would be the one color of light that my shirt was not absorbing, but was instead reflecting back into your eyes. So light and reflectance and transmission can be kind of tricky, right, to understand. And it's tricky to understand for fish too. So here are some common fish lures. This is what they look like in full spectrum light, like if you had them out here in the classroom. But if you put them deep in an oligotrophic lake, that's what the fish would see. Okay, so some of the colors are turning almost black. The white doesn't look white. In fact, the white looks blue and the green looks yellow. It's kind of weird. If you put them in a mesotrophic lake, this one just goes all white, right? And the blue here really turns black. And then if you put them in a eutrophic lake, then, this one almost goes white. Anyway, so the fish lures are often, they're built more for humans and what we think looks cool than what the fish actually would see underwater, given the wavelengths of light. This is also why if you're a diver, so if you go diving, you have to take your own full spectrum light with you, like a flashlight, because when you get underwater, everything just looks blue, right? Because you're most likely in the deep ocean, which is oligotrophic. But if you shine a full spectrum light on the coral reef, then all of a sudden you can see the beautiful colors, right? All right, the last few slides are about heat balance. And heating, cooling, and water movement all influence the temperature of water. This is really important in lakes that go through what's called a thermal stratification. So changes in temperature then can also cause water currents. So right, the movement of the water can change the temperature of the water, but the temperature of the water can actually cause water movement. So there's this feedback going on. And in the summertime, the top of a lake warms up, but the bottom of the lake stays cool, and you get what's called a thermocline. And the stratification actually is very stable, and it will keep the water from mixing in a stratified lake until the water temperature at the top cools down enough in the fall that then all of the water becomes close enough to the same temperature, and you get this mixing effect. So heat diffusion is also a thing. So everything we learned about diffusion earlier in the lecture applies to heat diffusion as well. And we can calculate the heat diffusion flux using, again, a modification of Fick's law. So J sub Q is the heat flux, and it's equal to a coefficient of thermal conductivity, K, and then a difference in temperature divided by the difference in distance. So it's very similar to the diffusion calculations that we did for nutrients or pollutants or something like that. And heat diffusion is greatest with large temperature differences and small distances, all right? And heat flux in an aquatic system, heat can be gained by solar radiation, by diffusion of heat from the atmosphere or from the ground, by warm water flowing into a system from precipitation or groundwater or lake water. But heat can be lost by reflection of that heat energy from the water surface, back radiation, by evaporation of the surface or from plants growing on the near the water, by diffusion from colder ground, and by cold water flowing into a system from the hyperrheic zone or from the groundwater or from the bottom of a deep reservoir. And also from evaporation from plant surfaces or shading by plants, riparian plants, or condensation on plant surfaces. So a lot of stuff can influence the heat flux in a stream system. And then here's a picture of the Colorado River, one of my favorite places on earth. I usually get to go down the river once a year as the ecologist on the Grand Canyon rafting trip. We'll see if it happens this year or not. But this is Glen Canyon Dam. This is Lake Powell behind it. Really deep, cold water in a system that's used to getting warm, muddy water. This is what the Colorado means red, red colored in Spanish, and that was the color of the water. Sometimes we still see that color during flood stages, but most of the time the Colorado River now looks green like this because of dam releases from deep under Lake Powell. It's also much colder than it should be, and this has caused all kinds of problems for native fish in the Colorado River. All right, that's it. See you next time.